Hello dear students, welcome to the channel and welcome to this signal and system playlist in which we are discussing about the sampling and reconstruction of a signal in detail. And up till now we have discussed about the sampling, what basically sampling is. We have discussed about a theorem known as sampling theorem. In previous class we have discussed about interpolation and different types of interpolation in detail. We have discussed about reconstruction of signals using low pass filter as well, and we have discussed about the different type of interpolation like zero hold and first hold or linear interpolation. So today we are going to discuss about aliasing or fold over error, which is, by the way, happens to be my favorite topic in this subject, and very interesting topic as well for those who are enthusiasts for computer vision, image processing, such things. So before I get to today's class, the understanding of previous class is prerequisite because I would be using some of the words. So if you have watched previous videos, it would be very beneficial for you. In case you haven't, you can check it out on the top right hand side corner of your screen. The link will be flashing on the top right hand side corner of your screen, and you can click on it on the I button and you can just watch the videos. Now that out of the way, even if you don't have, I would try my best to make you understand, but if you have understood it, then it would be better. Now that out of the way, let's get back to aliasing. So basically, what is aliasing? I have given the definition, but I will come to that. I've given the definition in this line, but I will come to definition slowly. First, let me tell you, if I'm having a signal, original signal x of t, which is not strictly band limited, and if the sampling frequency is less than 2 omega, then this aliasing phenomena or fold over error is observed in my signal. So in this kind of error, aliasing or fold over error, the adjustment uh, of signal takes place. I would show you the image, you would get better idea. But what exactly happens is that the adjacent spectrum in this spectrums in one spectrum of the sampled signal will get overlapped. And when this will happen? When the frequency is less than 2 omega, right? How? So see, when the frequency is less than 2 omega, then this will happen, this will take place, right? So uh, you can see here clearly overlap over here, right? See, overlap, actually we have rounded it over, so there is an overlap of signal. So signal basically x of t is not strictly band limited signal, but the spectrum of x of t is something that you can see in this image. Here we have the spectrum of the x of t, as you can see. And we take another discrete time signal x delta of t, which is the um, basically a discrete time signal. And when we take the spectrum of that, you can see it here, x delta of t spectrum. So that is nothing but this sum, this figure is basically nothing but the sum of x of f and infinite number of frequencies shifted replicas of the original signal, as I was saying earlier. Now if we consider two replicas of x of f which are centered about the frequency fs and f minus fs and minus fs, sorry, fs and minus fs, and if we use a reconstruction filter with its band pass extending from minus fs by 2 to plus fs by 2, so minus fs by 2 to plus fs by 2, then you can clearly see here in the output you are getting some distorted versions, we are getting some overlapping, right? So output will not be clear version of original signal. It will get some, you will get some distortions, and this distortion are occurring because of the overlapping of this adjacent spectrums. Now due to this overlapping, it is seen that the portion of the frequency shifted replica, this replica, looks like it has been folded over. See, if I fold this one over, then it will look like this, right? It is folded over inside the desired spectrum, and because of this reason it is also called fold over phenomena as well, right? Fold over error. And because of this fold over, the high frequency in my x of f are reflected into the low frequencies x delta of f, right? So and by the way, that's what you can see here. The high frequencies are getting reflected in the low frequencies. See, we are not getting exact curve. See, right? So how now if I want to define the aliasing, how would I define it? So the phenomena of high frequency in a spectrum of the original signal taking on the identity of the lower frequency in the spectrum of the sampled signal x delta of t, which happens to be, is called aliasing or the fold over error. Okay, so basically your high frequencies, rather I should call it high frequencies are taking the identity of lower frequencies, and because of that, what happens, we lose some information, right? When you reconstruct your signal, some of the information from your original signal will be lost, and that is why aliasing is not very good for any type of signals, be it images or any other type of signals, right? So how do we get rid of this aliasing? How can we eliminate it? So by the way, there are two ways to eliminate aliasing. First one is of course by using anti-aliasing or pre-aliasing filter, and the second one is using sampling frequency of fs greater than 2 omega. Now let's see both of them in detail. Okay, the first one here is by with the use of anti-aliasing or pre-aliasing filters. Okay, so simple thing you have to do if you want to avoid the aliasing, just use a band limited low pass filter and pass the original signal of yours through it, and just and do it before doing the sampling, right? And you will get rid of aliasing. So this band limited low pass filter will have some limited cutoff frequency, which would be around omega, and therefore it will strictly band limit your original signal before the sampling process takes place. So that is why this filter is called anti-aliasing filter or pre-aliasing filter, because it is done before the sampling takes place, right? Pretty much simple. Second one is by using the sampling frequency fs greater than 2 omega. So if I want to avoid the aliasing, I can simply increase the sampling frequency fs to great extent, right? I can take the value of sampling frequency too high, greater than 2 omega, and just by doing that, even though x of t is not a strictly band limited signal, the spectrum will not get overlapped. As you can see, I'm taking frequency too high, so here see, there is a there is a guard band. It's called guard band. The difference between two frequencies, it is guarding your signal from getting overlapped, so it's called guard band, and that guard band is used to avoid the aliasing. So it is getting created between two adjacent spectrums, and it will prevent aliasing to happening. Now there is something I want to talk about which I have not mentioned in the presentation, which is Nyquist rate and Nyquist interval. So what is Nyquist rate? is when the minimum sampling rate of say 2 omega samples per second for a signal gets produced with maximum frequency of omega hertz, then that rate is called Nyquist rate. Okay, so I will tell one more time. The minimum sampling rate of 2 omega samples per second for original signal x of t having maximum frequency of omega hertz is called Nyquist rate. And then we have something called Nyquist interval. So the reciprocal of this Nyquist rate, which would be of course 1 by 2 omega, because it was 2 omega, right? So that is called Nyquist interval. And of course because it is a interval, then the unit of this interval will be second. So it would be 1 by 2 omega second. Now let's see what are the effect of non-ideal reconstruction filter takes place. So we do have to pass the sampled signal through a reconstruction filter in order to obtain the original signal back from the sampled versions, right? And the reconstruction filter is a low pass filter. We saw it in last class. So it is expected to pass all the frequencies in the range of minus omega to plus omega, correct? And this is because the original signal x of t is a band limited signal, right? Band limited signal, the band is omega, so it will go from minus omega to plus omega. So its frequency response would look something like this. It is going from minus omega to plus omega, right? That would be your reconstruction. And this is the frequency response of an ideal low pass filter as well. But what happens in the practical cases? Because it is not practically possible to realize an ideal low pass filter, right? In reality there is nothing like ideal, so you have to find the practical solution for it. So a practical low pass filter with a frequency response as shown here with fs plus omega and fs minus omega is shown here. See, and it is possible to use practical low pass filter without introducing any distortion due to presence of guard bands between adjacent frequency spectrums. As you can see here, we are having guard bands here as well, and that is why it is necessary to have the frequency greater than 2 omega, right? So pretty self-explanatory thing to understand. When we are taking frequency f, then it will be minus omega to minus omega to omega, which was just like this ideal case. But in case of practical scenarios, fs plus omega and fs minus omega will be there, and because of that you have to take the guard band, right? Now let's discuss about the quadrature sampling of bandpass signal. So basically the sampling theorem for the bandpass signal is a little bit different from my low pass signals. So if I'm having a bandpass signal, let's say I'm having a bandpass signal called x of t, and if it has maximum bandwidth of 2 omega hertz or 2 w hertz, it can be completely represented in its sampled form, and it can be recovered back from the sampled forms if it is sampled at a rate which is at least twice the maximum of the bandwidth. Okay, repeating one more time, a bandpass signal having a maximum bandwidth of 2 omega hertz can be completely represented in its sampled form, and it can be recovered back from the sampled form if it is sampled at a rate which is at least twice the maximum bandwidth. Okay, so that was the sampling theorem for the bandpass signals. Basically, it is a statement of the sampling theorem for bandpass signal, and using that we are going to discuss about the quadrature sampling of bandpass signals. So and basically the quadrature sampling for bandpass signal is only for the uniform sampling of my bandpass signals. It actually is a natural extension of the sampling of low pass signals, and we have discussed about the low pass signal sampling earlier. So in this case, we do not sample the bandpass signal directly. What do? Instead of sampling the bandpass signals directly, before sampling, what do? We represent the bandpass signal in terms of in phase and quadrature components. Remember DQ component? No, if you have studied about the DQ component in machines, we do something like that here as well, right? We will have in phase and quadrature components, which we call xi of t and xq of t respectively, which you would be seeing here, xi of t here and q of t here. So the in phase and the quadrature components can be obtained by multiplying the bandpass signal x of t by cos 2 pi fct and sin 2 pi fct, just like we do in the dq axis, and then by suppressing the sum frequency component by the means of low pass filter, as you can see here, right? So first take your signal, when you multiply it with 2 cos 2 pi fct, then you will multiply it with sin 2 pi fct, then you will make your signal go both of make your both of make your signals both of the signals go through the low pass filter, and what you will get will be xi of t and xq of t, right? Which are basically in phase and quadrature signals. Now if my xi of t is in phase component and xq of t is quadrature component, then we can also compress the band pass signal in terms of xi of t and xq of t, right? So how do we write it? It's pretty simple from this figure only. It would be simply the subtraction of both of these signals, which basically will be xi of t cos 2 pi fct minus xq of t sin 2 pi fct, right? So, and as I've told you earlier, that we are assuming that fc is greater than w or greater than omega. It is found that xi of t and xq of t will be a low pass signals extending from minus omega to plus omega, right? The spectrum of in phase and quadrature component would be minus omega to plus omega, or minus w to plus w. Then both the in phase and the quadrature components will be separately sampled. What would be rate? Of course it would be 2 omega or 2w samples per second, and by this we will use switches SW1 and SW2, as you can see here, SW1 and SW2 for xi of t and xq of t. Now in order to reconstruct the original band pass signal from the quadrature sample version, we first have to reconstruct the in phase component xi of t and the quadrature component as well xq of t from their respective sampled version. What were the sampled versions? So x1 and ts and xq and ts, right? And for that, what do we use? Of course we will use reconstruction filters, we studied in the previous class. So we'll be using reconstruction filters. Then we will have xi of t, xq of t, and just simply add them together and you will get your final original signal back, right? Just multiply them with cos 2 pi fct and sin 2 pi fct, just like we did earlier, and then add both of them together and you will get your original x of t signal back as it was. So it is basically the inverse process or reverse process of quadrature sampling here, right? So that was the quadrature sampling of your band pass signals, and I think that is also very much self-explanatory. You can understand it from the images itself. It is very basic and good to know, like good to understand, easy to understand things, right? So now that you have understood the quadrature sampling of band pass signals, let's discuss some of the examples. right? See this one. It says the bandpass signal has a spectral range that extend from 20 kilohertz to 82 kilohertz, and we have to find the sampling frequency fs. You have the range, you have to find the sampling frequency. Now you have f1 and f2, so you will get the bandwidth, right? You just have to subtract it from one from another. So 82 minus 20, the bandwidth would be 62 kilohertz. Now what do? You take 2w, right? So 2 into bandwidth, 2 into 62 would be 124 kilohertz, correct? Then one more thing, whenever you do sum, notice that either of your outside and inside ranges, if they are connected harmonically or not. So here see, 20 and 82 are not harmonically related to each other, right? So f1 and f2 are not harmonically related to each other, and hence we have to use general bandpass sampling theorem, right? So what is the general bandpass sampling theorem? You take for value of k, what do? You take the higher value of frequency divided by the bandwidth, which is basically 82 by 62, and whatever the output you get, you will take only the integer of it. So and that would be the value of your k. So your value of k would be 1. And for the sampling frequency, what do? You take 2 times the maximum value of frequency divided by the value of k which you just found out. So 2 into 82, you will be dividing it with 1, and the answer will be 164 kilohertz. That would be your sampling frequency, right? Now let's see one more. So 100 hertz sinusoidal is sampled at 140 hertz and 35 hertz, and we have been asked to find aliased frequency in each phase, right? So we have the sine wave. The frequency of it is 100 hertz. Now see the first image, right? See the first image. You can see this one is the spectrum of your original signal. It is having 100 hertz frequency. Now as it is a sine wave, and the spectrum is 140 hertz, because it is getting sampled at 140 hertz, of course. So you will plot 140 here and 140 here. You can write the 240, it is not necessary to write, but you can also write it if you want to, right? And you will get the peak, almost semi peak, not exactly peak. Peak will be at 0, semi peak at 140, right? So make sure your signal is symmetrical on both the sides, because it is a sine wave. Remember, sine wave is symmetric. Then your reconstruction filter. In previous class we studied the reconstruction filter, and the spectrum of it is a rectangular wave, so it would be rectangular. And by adding them, what you will get? You will get the final output, right? Your final filtered output would be this, because your reconstruction filter is of 100 hertz, right? Because your original sinusoidal signal was 100 for 100 hertz. So that would be your filter output, and these would be the unwanted frequency components which are generated because of aliasing. This will get overlapped here, right? So you have to avoid it. The second is 35 hertz. So let's try to see for the 35 hertz as well. Again, my original signal is sampled at 100 hertz, so you will write 100 hertz here. Reconstruction filter will remain same, but the sampling, right? It is sampling is happening at 35 hertz, so the spectrum of sampling would take place at 35, right? And again, make sure to make it symmetrical. And filter, when you apply the filter, you will cut out other frequencies. You will only left with these frequencies, and these frequencies would be the unwanted frequency components, right? Plus 35 hertz and plus 65 hertz would be the unwanted frequencies. Also 100 hertz as well. These would be unwanted frequencies which are getting generated because of aliasing. Now let's see one more. So it is asking the signal x of t, which is equals to cos 5 pi t plus cos 10 pi t, is instantaneously sampled at the interval between sample ts, and we have been asked to find the maximum allowable value of ts, and we are we have been asked to reconstruct the original signal x delta of t is passed through the low pass filter and find the minimum filter bandwidth to reconstruct the signal without the distortion. So now first, you know what is your original signal, right? Cos 5 pi t plus cos 10 pi t. So as you can clearly see, there is a plus sign and there is only one plus sign, which means there are two frequency components present in the spectrum of x of t. Which two of are there? They are this 5 pi t and 10 pi t, right? And based on that, when you calculate it, basically in order to calculate, you just have to inverse it. You will get what you will get: 5 hertz and 2.5 hertz. So what would be the minimum sampling frequency? 2 into maximum, which means 5 into 2, right? F1 would be 2.5 and F2 would be 5 hertz. When you draw the spectrum, you will get the values, this 2.5 and 5. So 5 into 2, which means 10 hertz. So maximum allowable value of TS would be 1 by 10, which means 0.1 second. And the minimum bandwidth of ideal low pass filter for reconstruction would be the original bandwidth itself, right? What is the original bandwidth? So original bandwidth would be 5 hertz, right? Because your signal is how far your signal is going, right? What is the bandwidth of your signal? What time is it taking? So just 5 hertz, right? So that's your answer. Now let's discuss about A to D conversion, which is very important if you are working with digital signals. So for all the digital communication systems, the digital conversion is very important. And what is the principle of A to D conversion? So the process of converting my analog signal to digital signal is known as digitization, and we call it A to D conversion as well in short. So in this conversion process, the input analog data is converted into equivalent digital signal, right? So as you can see, my input signal is getting converted into digital signal, analog signal is getting converted into digital signal using A to D converter, right? And in order to carry out this transformation, one has to follow the sequence of operations such as sampling, quantization, encoding. Whole process you have to follow, and then you will get the A to D conversion, right? So the process is very essential for the digital communication system. If you want to do PCM or DM, pulse code modulation or delta modulation, this process is very essential. Now here you see, this is the block diagram of analog to digital conversion or A to D converter. You can achieve your A to D conversion by following these steps. First, you take your original analog signal, which maybe which may can look something like this. Then what do? You do sampling. You take samples. Once you take the samples, what do? You quantize your signal. You do the quantization of your signal. By quantize after at the end of quantization, your signal will get quantized, and it will look something like this, probably. We are going to discuss quantization in detail, so there is no need to worry about it. In the very next class, we are going to discuss quantization in detail. And at the end, you have to encode your signal, right? In order to convert your signal into a digital signal, you have to encode it. whether you want to convert it into the binary, hexadecimal, octal, octal number. So you have to convert it, right? So the system will contain these three blocks named as sampling block, quantization block, and encoding block. And the message signal can be analog or digital type, and an analog signal can always be converted into a digital signal very easily. Now what happens in this sampling block? So analog signal is applied at the input of the sampler. This can also be called sampler, by the way. So the sampler is basically a switch which samples the input signal at regular interval of times and will produce the discrete version of your input signal. Then you have the quantizer, which basically does the quantization. So what is quantization? It is basically a process of approximation, or you can call it round off of your signal, right? Round off is not exactly appropriate word, but to understand it you can use it as well. So quantization process approximates each samples to its nearest standard voltage level, or whatever the signal is, its nearest standard, that quantity level, which level is basically known as quantization level, and we get to the approximated value of the sampled signals at the output of the quantization process, right? And normally the number of quantization level is very finite, and generally it is into the power of 2, right? So it goes from 2, 4, 8, 32, 60, 64, 128, and so on. The last one is the encoder. So basically encoder converts each quantized sample into the separate code, which is word of which can be the word of n bits, it can be different number of bits, and then the output of the encoder will get digital code into the words, right? So that is the A to D conversion process here of yours. In the next class we are going to discuss about the quantization process, and most probably we will wind this chapter up as well. So from the next week we can start the very last chapter of the coursework. So if you have any doubts, queries, please feel free to mention them in the comment section below. It can be related to this, or it can be related to any other thing of signal system. Just mention them in the comment section below. If you have any questions, or if you have any feedback for the videos, every feedback is very valuable to us. Please mention the feedbacks in the comment section below as well. I will replying you as soon as possible, as many as possible. So we will wrap this lecture here. I will be seeing you next time. Till then, take care of yourselves, and thank you very much for listening. Goodbye for now.